Hello and welcome back to another video in the Introduction to Memory Forensics series. In this video we're going to talk about genealogy. No, not your family tree, rather we're going to talk about a different family tree involving Windows processes, some of which are shown here in Process Hacker. First, a couple of side notes. You may be wondering why this video is part of the Memory Forensics series instead of the Windows Forensics series. Technically, it could fit in either. However, we're going to be using volatility a bit later and looking at a couple of memory images, so I've chosen to categorize it in memory forensics. And secondly, if you haven't yet watched the other videos in this series, I would encourage you to do so. As an incident responder, one of the things you need to be able to quickly do when looking at a list of processes is immediately spot things that don't look right. As we saw in previous videos in this series, this could include things like an svchost.exe process that has a parent other than services.exe, or the presence of more than one lsass.exe process. So we're going to take a look at the core processes that are found on every Windows system, the processes at the very heart of the operating system that control the most basic functions, including providing the Windows API, the ability for us to authenticate, and even the ability for us to interact with the GUI. In addition to knowing the parent-child relationship of these processes, as you see here, we also need to know how many instances we should expect to find on a normal Windows system, the approximate start time of those processes relative to the system boot time, and the full path to the process executable on disk. We'll start with a visual representation of these processes and their hierarchy, and cover all of this basic information. Then we'll take a look at a memory sample acquired from a normal Windows system. Obviously, we have to know what normal looks like if we have any hope of finding abnormal. And then finally, we'll take a look at a memory sample acquired from a Windows system that has been infected with malware. Using our newfound knowledge, we'll then spot the discrepancies. So let's get started. You're looking at a poster from SANS called No Normal Find Evil. This is actually one of my go-to resources because the information presented here is vital when analyzing a potentially compromised Windows system. I'll include a link to this in the video's description. We're going to be referring to the content contained herein throughout this section of the video, so if you'd like to pull up a copy and follow along, that might be beneficial. As you can see, there are numerous processes listed starting with system, and for each we see a collection of important data including the image path, the parent process, the number of expected instances, the associated user account, the start time, and a description. In the center, you'll see a graphical representation of the process hierarchy as seen within Process Hacker. I've actually recreated this graphical representation in a different format, and we'll be looking at it as we analyze each of these processes because I think it's a little bit easier to read. Now you're looking at the diagram that I've created showing these same Windows processes. I'll provide a link to this in the video's description if you'd like to download a copy for yourself. Let's take a look at each process, starting at the top with System. The System process is one with which you're probably already familiar. The image path for the System process is actually NA if you refer to the SANS poster, and that's because it actually has no executable on disk from which this process is spawned. In other words, there is no system.exe or something like that. It has no parent process, as you can see. The number of expected instances is 1. The user account associated with it is local system. The start time is at boot time. And as far as our description, the system process is where we'll find mostly drivers, as well as implementation of our kernel mode threads, and the kernel executable itself, ntostrnl.exe. Underneath System, we have smss.exe, which is our session manager service. Its image path is system root, which of course is typically C:\Windows, system32 smss.exe. Its parent process is of course system. The number of expected instances is 1 for the master instance, and another for each child instance per session. We'll talk more about this in a minute. The associated user account is local system. The start time is within seconds of boot time for the master instance. Now the session manager process is responsible for creating new sessions, as you might imagine. The first instance creates a child instance for each new session. Once the child instance does its work by initializing the new session, which means it starts the client-server runtime subsystem, csrss.exe, which we'll talk about in a minute, and wininit.exe for session 0, or winlogon.exe for session 1 and higher, the child instance exits. That's important, and you'll see why in just a minute. Underneath smss.exe, we find csrss.exe, wininit.exe, and winlogon.exe. As mentioned, csrss.exe is the client-server runtime subsystem. Its image path is system root system32 csrss.exe, and its parent process is smss.exe. However, there is a caveat, and this is why you find the dotted line here. It's actually created by an instance of smss.exe that exits, so when you're analyzing this, the tools usually do not provide a parent process name, so that's important to remember. The number of expected instances is 2 or more. The user account associated with this process is local system. The start time is within seconds of boot for the first 2 instances, that's session 0 and session 1, and the start times for the additional instances occur as new sessions are created, but as the poster mentions, there are often only sessions 0 and 1. So the client-server runtime subsystem is a user mode process that's responsible for implementing most of the Windows API and providing a lot of other Windows features that you can read about on the SANS poster. Next, we have wininit.exe. Its image path is system root system32 wininit.exe. Again, the parent process is smss.exe, but again, it's created by an instance of smss.exe that exits, so once again, our analysis tools usually do not show a parent process. The number of expected instances is 1, the user account associated with it is local system, the start time is within seconds of boot time, and this service is responsible for starting our key background processes within session 0. So it starts our service control manager, which is services.exe, as you can see here, as well as the local security authority subsystem service, lsass.exe. Services.exe has an image path of system root system32 services.exe. Its parent process is of course wininit.exe. The number of expected instances is 1. The user account associated with it is local system. Its start time is within seconds of boot time, and as you might imagine, services.exe is responsible for implementing our unified background process manager and our service control manager, i.e. it manages our services that we find on our Windows systems. Next up, we have svchost.exe, which is a favorite of malware authors because of its ubiquitous nature. On a Windows system, we could expect to have numerous svchost.exe processes running at any given time, so malware authors will often take advantage of this by creating rogue svchost.exe processes located outside of the expected path, or they'll even use common misspellings like svchost.exe. The image path should be system root system32 svchost.exe. If you find an svchost.exe process outside of this path, you'll definitely want to investigate. Its parent process should always be services.exe. The number of instances can vary greatly, but again, you could typically have 5, 10, or even more. The user account also varies depending on the particular svchost instance, but it will typically be local system, network service, or local service. If you find an instance running under any other account, you should investigate. The start time is typically within seconds of boot time. However, services can be started after boot, which means that there can be svchost.exe processes that are started well after boot time. Now, this particular process is called the generic host process for Windows services, and basically it's used for running service DLLs. There are also a number of parameters after the -k parameter, and some of these include things like BT SVCS, DCOM launch, RPCSS, and several other ones that you'll note on the poster. These -k flags are something you'll definitely want to look for because having those not present or having unexpected values present there can also be a sign of a compromised or non-legit instance of this particular process. Moving on to taskhost.exe. Its expected image path is system root system32 taskhost.exe. Its parent process is of course services.exe. The number of expected instances is 1 or more, and the associated user account can vary. 1 or more may be owned by logged on users and/or by local service accounts. The start times here are a bit nebulous and can vary greatly. Whereas svchost.exe is the generic host process for Windows services, taskhost.exe is the generic host process for Windows tasks. So think scheduled tasks, for example. This process runs in a continuous loop listening for something called a trigger event, which could be a defined schedule, a user logon, a system startup event, or something of that nature. And lastly, under wininit.exe, we have the previously mentioned lsass, lsass.exe. This is our local security authority subsystem service. Its expected image path is system root system32 lsass.exe. The number of expected instances is 1. If you ever encounter more than one lsass.exe process on a system, that is definitely not legit and you should immediately investigate. The associated user account is local system. The start time is within seconds of boot time. And lsass is responsible for authenticating users on our Windows system. It is a critical process, and in fact, if it crashes, the entire system will crash. winlogon.exe has an expected path of system root system32 winlogon.exe. Like csrss.exe and wininit.exe, its parent is smss.exe, but it's created by an instance of smss.exe that exits, so our tools usually do not provide a parent process name. The number of expected instances is 1 or more, the associated user account is local system, and the start time is within seconds of boot time for the first instance, which is for session 1. Start times for additional instances will occur as new sessions are created, which is typically through remote desktop or fast user switching logons. WinLogon will actually handle our interactive user logons and logoffs, and it launches logonui.exe, not pictured here, which accepts our username and password at the login screen and then passes those credentials to lsass.exe, which we just discussed, to validate them. Now, userinit.exe is only mentioned on the poster within the explorer.exe process information, but I've added it here because it is important. This particular process will specify the programs that winlogon runs when a user logs on. So by default, winlogon runs userinit.exe, which in turn runs logon scripts, reestablishes network connections, and then starts explorer.exe, which of course is the Windows user interface, the GUI with which we interact. And lastly, we have explorer.exe, which has an expected image path of system root explorer.exe. You'll note that it's the only process we've discussed thus far that's not in system32. Its parent process is userinit.exe, but just like csrss.exe, wininit.exe, and winlogon.exe, you'll note that it has a superscript indicating that it's created by an instance of userinit.exe that exits. So just as with those three processes, our tools usually do not show a parent process name. The number of expected instances would be 1 per interactively logged on user. So on a single-use computer system, that would be 1. But if you have multiple people logged on to a given system, then there would be 1 per user. The user account associated with the explorer.exe process would be that of the logged on user or users. The start time would also vary and would be that of the user's interactive login session. And of course, the explorer.exe process would provide us with access to our files and folders, and it's the GUI with which we interact. For the next two sections of this video, we're going to be using a Kali Linux VM. and on the desktop you'll notice that I have two memory samples, abnormal.mem and normal.mem. We're going to be taking a look at both of these using volatility. Specifically, we're going to take a quick look at the running processes within each image as seen at the time of acquisition. You'll notice that I've issued the command volatility-f normal.mem, and then I've run the image info plugin, which is designed to provide profile suggestions to us. Alternatively, I could have used KDBG Scan, which is designed to more accurately identify the correct profile to use. In our case, it isn't necessary because I already know that win10x64_10586 is the correct profile. So let's take a look at the processes associated with this normal.mem capture. We have several different options with regards to which plugins we can use to view our processes. For example, we could use pslist, pscan, pstree. In fact, we're going to be using pstree because it provides a nice hierarchical view that will enable us to quickly compare the results with what we learned in the previous section. So let's run volatility-f normal.mem. For the profile, it's win10x64_10586, and we'll simply type pstree at the end to invoke that particular plugin. This will take just a couple of seconds to run. At the very top of the output, you'll notice System, with a PID of 4. In fact, System always has a PID of 4. All Windows processes are divisible by 4. And in fact, if you look at this PID column, you'll notice they are indeed all even numbers and are all divisible by 4. You may be wondering why System isn't PID 0, and that's because PID 0 is reserved for the sudo system idle process. In fact, if you look at the pPID for System, it actually says 0. Underneath this, we have smss.exe with a parent of System, and a second smss.exe, which is a child of the first, which makes sense based on what we learned. We have csrss.exe with a parent PID of 404, which is smss.exe, so that lines up. Here's wininit.exe, again with a parent PID of 404, which is smss.exe. Here is a single lsass.exe with a parent PID of 500, which is wininit.exe. Here's services.exe, again with a parent PID of 500, which corresponds to wininit.exe. We have multiple svchost.exe processes, which is not surprising. They all appear to have a parent PID of 636, which is services.exe, which is expected. So at a quick glance, this does appear to be what we expect from a normal Windows system. In fact, let's pick on svchost.exe since I mentioned that it's commonly targeted by malware. We'll run pslist and actually grep for svchost.exe. And when we do, we'll be able to quickly take a look at the results and see that they are all indeed underneath the services.exe PID. And in fact, this is the parent PID column, and they're all 636. So again, that matches what we learned in the previous section. In the next and final section of the video, we're going to take a look at abnormal.mem, which, as the name implies, is a memory capture from a system that has some abnormal processes running. So let's take a look at that next. Okay, as before, the first thing we would normally do is run image info or KDBG Scan to determine the correct profile to use. In this case, I already happen to know what that profile is, so in the interest of time, we'll skip that. Let's go ahead and run volatility, specifying our abnormal.mem capture. And the profile is going to be win10x64_15063 this time. And we'll run pstree as before and pipe it through more. So let's give that a couple of moments to run. Okay, let's take a quick look. At the very top, we see System with a PID of 4 and a pPID of 0. We see smss.exe with a parent of System, as well as a child smss.exe with a parent of this smss.exe. Here's winlogon.exe with a parent of smss.exe. There's userinit with a parent of winlogon.exe. We have explorer.exe with a parent of userinit.exe. By the way, you'll note that FTK Imager is listed here, as that is the tool I used to acquire this memory capture. And if we continue to look down here, we'll see csrss.exe with a parent of smss.exe, another csrss.exe, wininit.exe. So far, everything looks normal. Here is the beginning of quite a few svchost.exe processes, all of which seem to have a parent of 732, and 732 is services.exe, so that's correct. If we continue to scroll down through this process list, it's actually on this screen that you'll find our rogue process. You can pause the video for a second if you'd like, but the answer is actually an svchost.exe process with a parent of 6288, right here. This is not legit. It does not have services.exe as a parent, and this would be a red flag for us. In fact, if we run pslist, as we did before, and grep for 6288, let's see what we have. Interestingly, we only have that one hit, which is the rogue svchost.exe process showing that parent. That would imply that the parent 6288 is not currently running. Now we could use another plugin called Scan, which will actually show a little bit more in-depth view than pslist or pstree, and actually show us processes that have since exited, but that's beyond the scope of this video. So that pretty much wraps up what I wanted to cover here. I hope that you will take a look at that SANS poster, as well as the accompanying diagram that I created, because this information is, again, very, very important when you're analyzing a Windows system. At some point, you'll have a lot of these memorized, and you'll be able to just look at a list of processes and say, hey, that looks suspicious, or that shouldn't be here. So that's the whole intent of this. So again, download those resources and use them, because they will help you in your investigations. As always, I would greatly appreciate it if you would subscribe to the channel if you haven't already, and please do like and share these videos as well. Thank you for taking the time out of your day to watch this, and I will see you in the next video.